Okay. Biologist.
Intensa.
The nice thing is that you who are not yet fully enjoying the intensive week, you have to, it's a bit of a different experience when you have to do exams during the lessons, at the same time that you're doing lessons. That's when it really becomes intense. At the beginning, you don't have that. Normal. You have lessons in the morning, and then you have lessons in the afternoon, and you have a lunch in the midday. But very often, you have lots and lots of exams. Anthony, yes. I'm Anthony. I did not manage yet to connect this morning. I sent you a message. Here in Rome. Okay. Okay, welcome. This morning was a very introductive thing that we did. No. Did you do general bioethics with Father Miranda? No? We already did that. We've already done that in the past. In addition to myself, what other professors are you doing? We have general bioethics and then history and philosophy of medicine. Father Ballesta?
Sì.
Yes. Okay. Regarding the difficulty of one of the difficult things of bioethics and the intensive week is that since it's interdisciplinary, you need to face very different issues that are topics that are very different from each other, and that require knowledge that's very different from each other. It's a little bit complicated. Then after a day of this type, you might ask yourself, what am I doing here? Why did I make this choice? And did my spiritual father send me here? Okay, and after a few days, this effect passes and it all mixes in your head and something good comes out. In the second year, those who survive it, they can give witness to that it is doable, it is feasible. Now, another page from our course material, you can enter. Okay, I put up there a text. I don't know if why it's not there. And I'm going to look at this. No. I, for example, gave you this text here. Can you see it? Biology and science of life and life sciences. Biology studies living beings. Okay. Can you see it? Can you see it on the screen? Yes. Okay. Perfect. Okay. It is an extensive text. As I said to you earlier, some texts will help you to prepare certain topics rather than slides that are a little bit more fragmentary. This morning, we did a beautiful introduction on the world of science and technology and their relationship with bioethics, and we tried to approach our course with an attitude of a realistic attitude regarding the contents of the course. That none of us tries to transform ourselves into biologists or molecular biologists. That's not what we're here, and no one presumes to do this. And in the exam, not even there. But we want to look at science and technology without falling into absolute optimism, which ends up turning into scientism, and we should also avoid pessimism, where we have the idea that we need to throw out all science and technology, that it is all inherently evil. Now, in the morning, we spoke of science and technology, that they are the result of, that they are part of our rationality, and John Paul II spoke of that. And then we mentioned a book that brought us to discover this type of science and how we can have a science in biology and the history of and the study of living beings that tries to seek in some way to find rules that these living beings have in common, and this it can make present to us that there's something more behind them, that we are in front of something in our rationality that we can find that we can see a reflection of a rationality that is discovered in the world that surrounds us. So otherwise, we do not have this rationality. It would be possible to do science and technology. Science and technology, which are often seen as against bioethics, or even with the living world of beings, that we can see that there is an order in what surrounds us, and that we are not just immersed into a pure chaos. And in particular, our science is a science of life. That is a science that studies living beings. And we can see that when we do a course of bioethics and environmental questions, the definition of life is something that biologists, that escapes biologists. When I studied biologists, no one dedicated any time to try to understand what life was in itself and what a living being was in itself. So these are themes that belong to the field of philosophy more, and the philosophy of science, which we will see more in the course of bioethics and environmental studies. Biology is used the developments of science in order to go and study what is infinitely tiny. This morning, we talked about the cellular material that all living beings have in common, the fact that they are made up of cells. As this text says, biology is a science because it studies characteristics of living beings. And one of the characteristics that we want to posit is that all living beings, all organisms, are made up of cells. Okay, I want to focus on that. Here you will find some information. We mentioned this morning, some of these things, and some scientific discoveries and technological discoveries in the development of the microscope allowed us to develop the science. These are images of the development of modern microscopes, and this is the cork tree that I mentioned that inspired the idea of the cell, the idea of this little cells of the cork tree, that they were living cells. And then structural functional elements. Another basic rule of the cell, of cellular theory, is that every cell derives from another cell, and all living beings are made up of cells, and each cell derives from another cell. And then we will study from this course and the course in genetics, and also the course of other courses that Father Ballesta will teach, and how these, we'll take a look at how these cells are made up, and that they have very similar structures. And like another characteristic of living beings is that which is the strangeness of we think of the world of physics, where we know the bodies that tend normally to chaos, to degradation, while living beings constantly maintain this order, which is proper to life. Not only are they maintained and are self-maintained, self-conservation, are conserved over time, but they maintain these characteristics, which are more or less constant over time. And those who study genetics understand that living beings have characteristics which are inheritance and change. Generation to generation, they change, but within certain limits. There is a certain constancy over time. There's something that permits these living beings to transmit these information from one generation to another, and therefore there's something within our cells that allows us to contain this information and to transmit them to following generations. And we also see that this is a constant for all living beings that we know. This information, it comes from a molecule which is DNA, which we'll see that it is the DNA molecule. As we said this morning, living beings and also cells must be able to react there is the process of metabolism to take energy and nutrients from the environment. And this morning we said that they cannot, that these characteristics is characteristic of all living beings, this exchange of information from living, from substance within and outside of the environment that surrounds it. This is the cell cannot be too big. This is the reason why the cell cannot be too big, because otherwise the internal volume of the cell would be very big, while the surface of exchange, the cell with the outside world would not be sufficient to guarantee sufficient rate of exchange in order to transfer substances from nutrients into the cell and waste outside the cell. Another characteristic that we mentioned is that the science itself, biology, concentrates on living beings that we can see, that is organs and systems, and the scientific discoveries have allowed us over time. If we look at these images, have allowed us to go backwards, that is to go to to scales that are more and more tiny. We can also go in the opposite. We can see for the infinitely small, like atoms, that all bodies on the Earth are made up of, that unite into molecules, come together in molecules. We're talking about infinitesimal dimensions under the angstrom level. And then we reach measures that we mentioned this morning of microns and nano and microns, and these reach the size of our cells. And cells collect with each other in pluricellular, multicellular organisms in tissues. They are groups of cells with a certain function. That's what a tissue is. And then cells need to adhere to each other and connect with each other. And then we have a compact tissue, and tissues also connect with each other with various functions, and they form organs. Organs carry out a certain levels of systems, and then this make up an organism, an individual which has a corporal frontier that separates it from the space that surrounds it. And though it's multicellular, a organism has its own unity, structural unity and functional unity. In reality, biology studies also studies beyond that. In the field of ecology, we can see this, that organisms do not live in isolated realities, but they live with other organisms of the same species. And this, here we can speak about populations of cats that live in Rome, for example. A population, we can speak of a population. And populations do not live alone either, in the sense that they live together with other living beings of different species, which are maybe very different from each other. In a zone, there are bacteria that have a little in a little lake, that there are plants of another. There might be trees that surround a lake and other animals that eat there, and a population of different organisms of the same species. And the communities of organisms make up the populations of different species, including the grass, the trees, and different animals of different sizes, and different species that live together with other species in the same place. They make communities. Communities, in turn, and this is a grouping of living beings of different species. They live in relationship with the environment in which they find themselves, and so in relationship with quantity of available water and climate and humidity, also the acidity of the terrain, and this is all an environment conditions, and all of these communities within those specific environmental conditions that takes the name ecosystem, and this is the objective study of ecology. Now, once ecology, at one time ecology was inside of biology, but in certain way we can say that the opposite has happened, that ecology contains biology. We could say this, that it is a science that studies living beings, but biology has ecosystems ecology studies ecosystems, which contains living beings and non-living beings. But biology just only studies living beings. No, organisms, populations, communities. All organisms, we said that they have these common characteristics of interacting with each other and to have a metabolism and exchange with the external world, environment. And you find this all inserted into this link in this capital of this book that I made available to. And now, let's say that scientific discoveries have allowed us to go in the opposite direction in this scale. That is to go to the level, down to the cellular level. We said something about cells. Now I need to share again the screen with you. Now I have to share the screen with you. It was here. This is our page, our web page. This is we just leafed through, we saw these two groups of slides, which talk about the cellular dimensions. You can see it. Okay. Okay, we were looking at this morning. I'm going to call up something that we were looking at this morning.
Il fatto che mi si è aperta un'altra finestra, non so che cosa riusciate a
I don't
vedere.
know what you're going to be able to see. On the slide, you can only see the list of course materials. Is that correct?
Nulla. Non si vede
No, we can't see anything yet. Okay, now we can. Yes, here it is. There it is. There it is. Okay. The slides, yes. Yes, you can see the slides. We said that this morning regarding the cellular dimensions. And now here I introduce an element that we will talk more about in the following days, in future days. Two classes of cells that are fundamentally different, which are, we said that all living beings are made up of cells, but we can distinguish two groups, two different types of great groups of cells without intermediate forms, that is with differences that will allow us to separate them from each other. In particular, what we will concentrate on now is this division that we mentioned earlier between cells that are called prokaryote or prokaryotic cells and eukaryotic cells. And all of these, between these two groups, we can find all 5 kingdoms, we could say 5 kingdoms. In this case, we distinguish 6 here on the slide, but they classify all of our living beings. But the principal distinctions are between cells of a certain type, prokaryotic cells, and eukaryotic type cell types. And animals are almost always made up of eukaryotes. We see the principal distinction that the name and prokaryote and eukaryotic names consist in the fact that prokaryotes do not have a clear nucleus inside of them, which is visible. But eukaryotic, here they have a nucleus that is very visible. Within this nucleus, we have the hereditary material. And one of the characteristics of the living beings is that they transmit their characteristics to the future generations. This is permitted by hereditary material, which is contained within the nucleus. Eukaryotic organisms include protists, funguses, plants, and animals. And what others are, some are unicellular, some are multicellular, but prokaryotics are always unicellular and fundamentally they're bacteria. Beyond the differences, between these two types of cells, and we'll see this over it's interesting for us to return to analogies between these groups of cells, in particular, to return to the basic elements. That is, the prokaryotes and eukaryotes have a similar chemical composition to each other. They are made of certain elements that start with an element that's called carbon, which is a fundamental element for both of them, for life in general. And they have a similar makeup and to a certain degree. And cellular biology and molecular biology speaks about this, and it studies all of these analogies. Okay, which makes us think also evidently that all living beings had some common imaginary ancestor. For example, cells are surrounded by a membrane, which is formed of proteins and fats, and cells transmit information from one generation to another through this molecule, which is the DNA, which is called DNA, deoxyribonucleic acid, and it is rather similar between prokaryotes and eukaryotes. Now, what is carbon? What are these molecules that prokaryotes and eukaryotes are made up of. We want to look at carbon, the carbon atom right now. You already can find all of this, as I said to you earlier. Find this in your online course material on upra.org. Now, if you look on my screen, if I open this one here, it should be the right one. Okay. Once again, can you see the slide? Yes, we can see it. Okay, perfect. Now we were saying that it's a group of, or rather, we'll go through them quickly, not only because we don't have time, but because, as I was saying to you, that what we want to stay in your minds is especially the ideas, the basic ideas. Now we were saying that all living beings are made up of cells, and there are certain common characteristics that cells have, and all cells are characterized by having a chemical structure which is very similar to and made up of certain classic molecules which are called macromolecules, which are rather big molecules, which you certainly have heard people speak about fats, which are called lipids, and proteins, and sugars, and nucleic acids, DNA. Because substances are for them to aggregate with each other and to put together. And okay, is there something smaller than these molecules? Yes. Smaller than these molecules are the elements that also these molecules are made up of. The elements are made up of the part of cell that we know, which is called atom. You'll find among the course material, you'll find some explanatory videos which deal with experiments that have been done. In particular, there is one that concerns what we talked about this morning, that the cellular dimensions. You find a video that explains to you which explains to you the dimensions of living beings. It's a brief video and explains the dimensions of the cell. It's rather it explains it very well, and it's a little bit of a long video. You'll find it, and it is called like experiment.
Serve appunto a capire
and it's useful to help you understand how small cells are. And this experiment that we can do it, it's an experience that's rather, and in these researchers show you how they prepare small proportions of a substance that's called agar. Agar. It's a kind of a gelatin. It's used in cooking in the kitchen, and they color these little decorations of red agar, and it's a coloring element, and they show you what happens if it's put into a solvent, and parity of time, these cubes of this gelatin that's very small, and they manage to be decolored. That is, the solvent passes from the outside to the inside, and it manages to remove the color. Clearly, the bigger cubes, no, in the sense that this also helps you understand how a cell, if the cell were too big, then there would not be time to, in our case, the solvent, but in our case, in the cell, we have various nutrients, etc., from the outside to the inside of the cell. And it shows how through this experiment that it helps you just see this concept will be more clear to you. Okay, you will also find a video there, which is a bit dated. It seemed that it was rather clear on the dimensions of atoms and how we imagined atoms, and it shows you there how a possible representation that is rather cute of how those who hockey players on ice, and they start to rotate around a position, a central position, and how our atoms, which are in our cells, which that make up molecules, and they're made. Okay, there's a central nucleus which is made up of certain elements that are called protons and neutrons.
I protoni sono dei piccolissimi
elementi very small elements that are charged. There's a charge, a positive charge, around this nucleus, the central nucleus of the atom. We see the rotation of a series of other small particles, which are called electrons. which have a negative charge. And the atom, normally, it ends up being neutral because it has the same number of positive and negative charges. And the negative charges are the electrons that rotate around the nucleus, while the positive charges are the ones that of the protons. And in the video, it shows how these skaters rotate around the nucleus in positions, stable positions, in fixed positions, like they were orbits of planets that rotate around, or the moon that rotates around the Earth. Or imagine that the image that you have is that there's a central nucleus and things that rotate around it. And there are certain courses that in chemistry we call them orbitals. The most simple or element that we find is the hydrogen atom, which has a single proton and a single electron that rotates around it, which always follows this orbit, or electronic shell, let's say, neutral, and then so it has a positive and a charge, a negative charge. Our carbon, which makes up a great percentage of living beings, which forms various connections between these molecules, is made in the following way. It has 6 electrons that rotate around it and 6 protons. In the description of elements, which are the famous table of elements, just want to understand certain things that happen at this level. Hydrogen, which we've just described, and then there's carbon and iodine, etc. Why are they presented in this way? Why are they depicted in this way? Electrons that rotate around our nucleus here that we see tend to obtain this element, a stable situation. Now, when does the atom reach a stability? Atoms are stable when the number of electrons that rotate around these orbitals is a precise number. In particular, we said that in our example here, in the hydrogen, we have Rome proton and just a single electron that rotates around it. If you look at the arrow, I don't know if you can see it. Okay. The first orbital, so to speak, which is the closest to the nucleus, is filled, and it renders our atom stable when there are 2 electrons which rotate around it. Because in order for this atom to be stable, there need to be 2 electrons that rotate around it. In the case of the hydrogen atom, that's not the case. So the hydrogen element alone does not feel very stable. Well, in our chain, we'll find that helium, which is one of the noble gases, has 2 electrons in that level, in that orbital, and 2 electrons are rotating, and they are saturated. Why? When there are 2 electrons, it cannot accept anymore. With 2 electrons, that atom, it finds itself stable, and in fact, helium, it does not react with others because it's stable that way. Hydrogen finds a situation of defect because it has only 1 electron that's rotating around, and it needs to do something in order to obtain this missing electron. So this thing that it needs to do in order to get to obtain to reach this stability, it is due to the fact that this orbital, that there are 2 electrons. When this first orbital that's outside of the helium is full, the following electrons, the atoms that have several electrons, have to occupy another space. This you see in the video. You see it very easily. See the electrons that rotate around the nucleus. And there's a bigger circle which goes around the nucleus, and it finds another position. Now, from the second orbital on, the stability is not reached by a number of 2 electrons, in that orbital, but 8 electrons will be necessary to achieve stability. We need 2 electrons in order to saturate the first orbital, so that atom will be full or saturated. And from the second orbital on, we will need 8 electrons on. In our carbon atom, we'll see how important it is for the building of life. It has 2 orbitals in its, okay, no, the carbon has 4 in its second orbital. 4 are not 8, evidently. So once again, carbon also is not stable as such, because it only has 4 electrons. And with this, in the second shell, it has necessity to acquire 4 electrons that are missing. It needs 8 electrons, which is the stable configuration for an atom in its case. In order to reach stability, an atom will tend to form bonds, which will allow to have at least 2 in its first orbital and 8 electrons in its second orbital. In the course material that I will leave to you, saturation is given by 2 in the first, and otherwise it needs to do bonds, create bonds. Through bonds, chemical bonds, like persons, should reach a certain stability when they bond with each other. What type of bond can we find? What you will find in this course material is that they can form different bonds which have force of cohesion and union, which are different from each other. In this image that you see here, find these 2 hydrogen atoms, which I said are not stable because they have just a single electron that rotates around them, and they will tend to share their electrons. Therefore, they will get very close to each other. They are too far from each other. They're too close. The positive nuclei will reject each other, will repel each other. Here we see stability. They share, so the electrons start to rotate around one and the other. So it's true that each of them have just 1 electron, but in they will constantly also have the other electron that rotates around it. This type of bond in which the 2 electrons are shared because they have not been taken from one atom from another or given from one atom to the other. They are simply shared. This type of bond is a very frequent bond in chemistry, and it's called in a symmetrical way. It's called a covalent bond. This is called a covalent bond. The atom of carbon, the carbon atom that you see here represented, has 2 electrons on the first level, which is stable, is saturated, and it has 4 electrons in the following shell. We said that it must seek to have 8 electrons in that level. So, for example, it can connect to 4 bonds with other carbon atoms. This is what we can see here. The electron, this material allows it to have 8 electrons in its external shell. This is what we see with C4. C5, sorry. Now between 2 atoms here. Now here you can find another possible situation with our atoms. Now we can look at them in 3 dimensions and how the bonds. Now we are supposing now between 2 atoms of hydrogen, since they are atoms of the same type, that they will have the capacity Let's think of it like magnets. There's a positive and negative side of magnets, since they have the capacity to attract electrons in the same way, because there are several atoms of the same type. Atoms of three uh, carbon atoms connect together with each other, which are H and H2. And two, okay, first we can see carbon dioxide atom, or molecule, sorry. But if this bond is covalent, which consists of sharing these electrons between two atoms we see put into play, it should be that these two atoms have the capacity to attract electrons, which are different electrons, and rotating around themselves with like a magnet. Let's suppose that students of a license, an intensive license in bioethics, that they will have different teachers. Some teachers will have the capacity to attract these students more than others. Maybe students that will do thesis to him. The same thing happens with our atoms. Certain atoms can have a force of attraction to electrons which are greater than others. This force of attraction takes the name of electronegativity. Electronegativity of atoms have this capacity that they have to attract electrons. If our bond is covalent bond, in which the electrons are shared between two atoms of the same type, obviously the electronegativity is the same, and therefore neither of the two atoms will attract this electron with a different force from the other. And so the electrons will rotate around the nucleus indifferently from one to the other. But if, on the other hand, if the bond is made of atoms that have an electronegativity that's different from the other, what will happen then? An extreme thing could happen, which will bring us to consider a different type of bond, which is called ionic bond, covalent bond. In a covalent bond, the two elements between our two atoms. But on the other hand, in the example that is depicted here, we have, for example, the atom of sodium, which has just a single electron in the first full orbital. In the second orbital, this is also full with 8 electrons. And then it has another electron, which is still rotating in the third orbital, which is a little bit more distant, just one, a single one. For that, for it to make a bond, it will have to give it to another hydrogen atom, or simply to lose this electron that it has in the final orbital. It's easier for you to enter into. Okay, you need to cut. Okay, now the chlorine atom in the external orbital, it has 7 electrons, and it just needs 1 to complete the shell. Now let's speak about electronegativity. Rather than putting these electrons in common with each other, which are found alone and isolated in the atom, what happens here is that the chlorine manages to attract with a lot of force that electron, and to the point of stripping it from the sodium atom. And what we see here, this is salt that we know. This is sodium chloride. This is the salt molecule. That's what ends up. This happens, and this is a kind of bond that is not the sharing of electrons, but one electron is completely taken away, stripped from the sodium atom in this case. Na is the symbol of sodium, and it is given to the chlorine atom, because this is why we have these symbols. Because what happens here is that our atom is a substance, so to speak, which is neutral, which has the same number of protons of positive charges as electrons, that is negative charges. But here we have a molecule, an atom that lost its negative charge. So it has one positive charge. And It's a sodium ion. This is what we call this atom. It is our atom of sodium that has lost one electron. Therefore, it finds itself that it has a positive charge because it has lost its negative charge. The chlorine, vice versa, has acquired a one further electron. It's acquired a negative charge with respect to the situation that it had before, of neutrality that it used to have. So our chlorine is uh, depicted as Cl minus because it has become a negative chlorine ion. It has a negative charge. It has become an ion. One has one more or one less atom. So it has a chair. So between them, we have a bond, which is called an ionic bond. An ionic bond. This is depicted here as covalent bonds. We have two atoms which share, would have the same affinity and the same capacity of attraction of the electrons, electronegativity, or similar electronegativity, and they share electron. But with ionic bond, an electron is stripped from one and added to the other. But what happens here? What happens when sodium is put into water? When our sodium is put into water, you know what happens. The salt tends to dissolve in water. And if the salt loses its taste, it begins to. What we see is this ionic bond is broken. What characteristics does water have? We have two explanatory videos. You can find it. It's almost romantic. But it's rather clear in another video that's a little bit more explanatory regarding the properties of water. Why is water so particular? Because it's a universal solvent, we call it, and it can dissolve. And there are certain substances that cannot be dissolved. Can you imagine certain substances that do not dissolve in water and do
L'olio.
not mix in it? Oh, oil. Exactly. These are substances that when we put them in water, they are not dissolved. This is why, for them, water is not a good solvent. What is water made up of? We said earlier that we have two extreme cases. For covalent bonds, the nucleus have a similar affinity for the electrons. Neither of them have the force of stripping it from the other. But the ionic bond is the opposite. Because of this difference of force, one of the two elements strips the electron from the other. But we can also have situations, and water is one of these, in which there's a difference of this force, attractive force on the part of the molecule towards electrons, but the difference is not so much to generate a ionic bond. This is called a covalent bond. It's a covalent bond. It's polar covalent bond. Or this means that our a water molecule, it's made up of these elements, two hydrogen atoms and one oxygen element, H2O. Among these, the oxygen has bonds, one with hydrogen and one with the other hydrogen atom. There are two covalent bonds, which we studied earlier. The electrons of hydrogen are not shared with the oxygen, and also they are shared with the oxygen molecule. And they rotate here around all the nuclei of these elements, these different atoms. But if we wanted to make a photo of a very brief instant photo of our molecule, we will realize something strange, because it is a covalent bond, but between different elements. Between these atoms, they have a attractive capacity towards the electron, which is different. The oxygen has, as we will see from this image, it has a greater electronegativity. That is, the oxygen atom is able to keep with itself the electrons more with respect to the compared to the hydrogen atoms. We think of our famous professor, who's capable of detaining students more than another. His students are from the bioethic faculties, which are shared by the various teachers, but some stay more with you than with another, and that's what oxygen does towards the electrons. It keeps the electrons more with him than the electron spends more time around the oxygen nucleus than the hydrogen atoms manage to keep the. No, if we manage to do this infinitesimally short instant of time, if we manage to could photograph a water at a molecule, we would see that our molecule in reality is asymmetric. That is, it has a point which is around the oxygen, in which it has a greater negative charge. Because the electron rotates around it for more time than it does around the hydrogen atoms. And therefore, there's a negative charge on the side. And the other side of our water molecule, on the side of the H's, it has a positive charge because the electrons are on the other side and the protons are more on this side. We could say that. This characteristic is a characteristic which is very important for water. And this type of covalent bond, which is a polar covalent bond, it's a polarized molecule. It has a pole which is more negative, and then on the one hand, and then a more positive pole on the other side. If we imagine, let's imagine in this water molecule, which is depicted more negative on this side and more positive on this side, which if it approaches, let's say what happens if it approaches another water molecule. One hand has hydrogen atoms which have positive side, and the chlorine side, which is, sorry, the oxygen side, which is more negative. We see here the same situation we see with our magnets. We have two molecules of water that are close to each other. The one side of the water molecule will tend to attach itself to the oxygen as if it were a magnet that attracts another magnet. I don't know if you understand from this image. Maybe it's a little bit difficult from these images, but you see how the water molecule is depicted as H2O here. Here, there's another molecule of water that's close to it, H2O. The depiction has this, recalls to mind this idea that this side is positively charged and this other side is negatively charged, and it tends to form a bond of attraction with the positive part and the other negative side of the part of the oxygen which is more negative. It tends to form a bond of attraction, like a magnet would, with a positive side of the other water molecule. And I think that this bond, which is depicted by this kind of attraction here, with the red line here, it is as if this hydrogen were kind of this is a rather weak bond that the hydrogen atom forms here. But in water, there are a lot of bonds like this, because among all the molecules of water, which are called hydrogen bonds, we call them hydrogen bonds. So we spoke of covalent bonds, and where electrons are shared, and ionic bonds, where an electron is stripped from an element to another. And this hydrogen bond, which is a bond of attraction, almost a magnetic attraction between two molecules which are polarized, which have one side that's more positive, one which is more negative. In water, for example, we form many hydrogen bonds like this. It's not a very strong bond and is easily broken. There are many hydrogen bonds here and there, but they are weak. This explains why, in order to break these bonds, this is what we do when we heat water to make pasta. We need to give a lot of energy for water to work. We need to heat up our pot of water, because we have to break these hydrogen bonds, which are not very strong bonds, but in water there are many of them. This explains also what happens when we put our salt into the water. So hydrogen chloride, and sodium chloride have magnetic chlorine and the sodium ion. One is negative, one is positive. These two ions in this attraction. There's another magnet that comes in, which is this polarized water molecule. So ions are surrounded. One The negative ones are surrounded by the positive sides of the water, and the positive ions are surrounded by the negative parts of the water. These ionic and the chlorine atoms are all the sodium chloride ions are broken with each other. Okay, one characteristic of water is very important, which we'll see now. It allows us to have in water a point of boiling point, which is very high, which is normally in the environment that it be water. And it also means that water is an optimal solvent, and it can dissolve many substances, not only salt, because it has this force of these polar bonds. Another characteristic that this type of bond has that when water it freezes, what happens? It decreases its density. If you put a bottle of water in the freezer, what happens? Especially if it's a glass. What happens? Have you ever forgotten to leave a bottle of water into the freezer? It expands, and it breaks the bottle. With respect to liquid water, ice it increases its volume. Ice has greater volume than liquid water. It is less dense. It floats on liquid water. That is another characteristic of water regarding the hydrogen bonds in the water. It means that in water, what is called surface tension. So there are certain insects that can rest on water because they create ordered bonds between the interface between the water and the air. This is the same explanation for which if our plants are very high, if there are no, there's our heart that pushes liquid. We manage to suck water from the roots up until the leaves that are 40 meters above, which we see in trees. And they're almost like a straw which aspire the water to, and it creates a suction, and it attracts the molecules of water because of surface tension, and the water can go up from the through the roots for tens and tens of meters for many. We see now what happens with ice. Now this image that you see here, these molecules, which are very concentrated, they are molecules of water that we see, and at room temperature, and there's a great thermal movement in between these molecules, and then what happens with ice? The hydrogen bonds are stabilized, and you see this image in the same proportion of water. In liquid water, there are many of these molecules. In solid water, in the solid state, in ice, the more ordered state, there are fewer molecules. So structure has expands, and but it is lighter because inside there are fewer molecules. It is less dense. In fact, ice floats on water, liquid water. It acquires volume. Why? Because molecules distance themselves from each other when they freeze. And so ice, if you put these ice expands, but with the same number of molecules. If it expands, but it has the same number of molecules, it means that if there are fewer molecules, it means it weighs less. It also means that if we have ice on that ice in a sea freezes, it always is on the surface. What happens is that if the ice is on the surface, it acts as as an insulator, and the liquid and the liquid below, it makes it much easier for life. Since water is a polar solvent, this explains to us how through ice and how life is possible on Earth. It explains to us how plants can draw up water for tens and tens of meters, and it also explains to us why water is so important and fundamental as a solvent. Now, I would like to go back and ask a question. There was a question that someone asked earlier of why salt does not dissolve in oil. I would like to understand well the difference between the molecules of oil and those of water. For this reason, what its structure is. Exactly. No. Now we're going to reach that. That's an important question, and we'll reach that question. Now, in this slide, which is a little bit more complicated, but it is important to remember this concept that there are certain substances that we call polar substances, that is, which have in some way they are electrically neutral. They have a polarity, that they have a part of the molecule of this substance which is more positively charged, and another part that's more negatively charged. Okay, water is a solvent, a polar solvent, because as I said earlier, water, the water molecule has a point in which it is more negative because of the presence of more electrons, and on the other side, which is more positive because of the absence of those electrons. For this reason, water can dissolve a variety of substances like salts, but it can only dissolve those substances which are polar, which have that characteristic, which have a charge which is negative on the one hand and a positive charge on the other. There are certain substances, however, like you just mentioned, for example, oil, which is a substance which is not polar. That is, it does not have this difference of charge, of electric charge from one side to the other. Since it does not have this polarity, it is an apolar molecule. It's a molecule that is not dissolved in water. So we will find, for example, here is this long chain of carbon is represented, and you will see it depicted here, and how it is a molecule that is made of many atoms of carbon. And you saw these carbon atoms of this crossing over. It has 4 bonds with a hydrogen
A
and
volte
oxygen bonds, and sometimes our carbon can form a double bond in order to connect itself to oxygen. This molecule is a charged molecule. It is polar. It's soluble in salt and sugar. Our oil, though, these are molecules which are non-soluble because they are not polar. They do not have capacity, since they do not have this difference of electrical charge from one side to the other. They cannot create hydrogen bonds. These magnetic attraction bonds, we can call them, and therefore our substance of oil does not dissolve. These characteristics which fats have is very important, because in our cells we find, and we will see this shortly and tomorrow especially, we see that in our cells that there are substances which are polar, and our molecules which are polar. They are hydrophilic, that they like water, that they have a friendship with water. They form a bond with water because they are able to form these hydrogen bonds with water. Therefore, the moment in which they are put in water, the water molecules break these are substance, and they form each of the elements of this substance, and they form bonds with it. There are substances, on the other hand, which we call non-polar substances or apolar substances, which are hydrophobic, that is, like oil. They do not like water, which do not mix with water, which are hydrophobic, which can be they are scared of water. Why are these important characteristics in our molecules? Why are these important to keep in mind? We will see that our cells are made up of proteins, but also of fats. Our cells will have a barrier which protects it from the external world, which separates it from the outside, and also separates inside of the cell with the external world of the cell. Inside of the cell is made up of substance of watery substances, like which make up the cytoplasm. What would be a good what will be a good barrier between a watery substance with a external? It's made up of substances that do not mix with water. The membrane that surrounds the cell must be made of substances that do not mix with water, which do not form bonds with water. In fact, the membrane of the cell is made up especially of lipids, that is, of fats, like oil. At the same time, though, we said that the cell should not be completely separated from the external world. Therefore, I surround the cell with a membrane, which is called plasmatic membrane, which is made especially of fats, so that it does not create a separation completely like oil is separated from water and will be separated from water. If I put a drop of oil in it, they tend to group with each other. But the membrane that's made up of fats like oil, they separate the cell from the external world. This separation should not allow into the cell, into this membrane that's made up of fats. They should be ways to communicate with the external world. Little holes in that membrane need to be there also to allow a certain substance to come in and go out to create pumps, chemical pumps that allow the cytoplasm to interact with the outside environment. Okay, here it is. We call these chemical pumps. Holes in the membrane. No. In the case of oil, with cells, skin cells, epithelial cells, skin cells especially. Why is oil good for those cells? For example, I don't know, like a cut, like a burn on our skin, for example. Why does oil seem to help it alleviate? I don't know. I can imagine. You can imagine that we have to be careful of thinking that fats and some as such are enemies of our body. That's not the case. Our okay, our cellular membrane, our cells need to be lubricated in a certain sense. Inside of the membrane of our cell, there is the famous cholesterol, which we are all scared of. Let's see, because if there's too much of it, and it is deposited in our blood vessels, and it renders the blood flow more complicated. But in a certain quantity, this is necessary because it renders the membrane of a cell more fluid. Like we put it into the freezer, like when we put antifreeze in our car, it allows our oil of our membrane to remain more fluid. We can imagine that the oil and the oils that we put make our skin more fluid and more can also form a barrier, a protective barrier. Because of that, plasmatic membrane is made up of, especially of fats. In some way, it helps that protective barrier. But the idea is, I cannot, unfortunately, respond to you with an exact way right now. That distinction is very important. I remind that to you. The polar substances are those which are made able to make bonds with water. We speak of hydrophilic substances, because they form hydrogen bonds with water. Apolar substances are hydrophobic. In general, fatty substances are apolar in general. Fats and the membrane are, in order to add a term which is complicated and difficult to remember. Sometimes we have hydrophobic molecules and apolar and hydrophilic, which are polar, and then we have amphibatic molecules. Many of us are these are amphipathic. Amphipathic means that, on the other hand, they are at a certain point. On the other hand, on the one hand, they are polar, and on the other hand, they are apolar. The presence of this amphipathic substances that have both characteristics of polar and apolar molecules, they pose important, interesting problems sometimes. When we study proteins, I think in 2 days we'll study proteins. We speak about, we'll discover that proteins are proteins which carry out many functions in living beings. They are structured, and they form the structure of the body and movement. If have enzymatic functions, they cause certain chemical proteins, carry them out because they have a certain form, and a certain shape in space. This shape of three-dimensional shape of proteins is due to the fact that they create bonds in the chain of the bricks that form our proteins. And these bonds are due to the fact that some elements of the membrane that they are more exposed to the water, and others that are hydrophobic, and they try to avoid water, and this means that the protein assumes a form that's a particular three-dimensional form, and it allows the function of the protein itself. Certain sides. Okay. Now, a curiosity question. I was asking myself if this quality of water, of being polar, if it is a motive for which we can ask ourselves of taking a lot of water because it has this capacity of this polarity. Is that possible? In reality, this is necessary for all living beings. That is, if you find it as one of the common elements that all living beings have is that we use the fundamentally the same. We all have the same elements: carbon and oxygen and hydrogen, but lots and lots of water, which is useful to carry out certain processes. The fact that it's useful as a solvent and it allows us to dissolve substances renders water an element that is essential for us. So therefore, we constantly have the case of water is useful for many things in the body. It also affects the kidneys and excretory. Okay, it has. Okay, now in these two videos, it explains these characteristics. I said earlier. One of the videos is more sentimental and a little bit romantic, and another is more explanatory. There are two different types of videos that explain how all of this works. Life would have been impossible without water as we know it. Life as we know it on Earth would be impossible without water. It has very particular characteristics. Now, in these two groups of slides, I would say that it's not so useful for us to remember too much more of this. Okay, now we'll return to this. Another example of our fats of an amphipathic molecule. Amphipathic. On one hand, it's not polar, the fatty part of the molecule, which is not as, this is a fatty acid. It's a non-ramified chain of carbon atoms and hydrogen atoms. And this part here is COOH is a polar side, which mixes well with water. Lipids, that is, our fats in the presence of water will tend, if there's a substance done in this way, it allows us to put this head, so to speak, here, which is polar, in contact with water. You see it's depicted in red, and this is the surface of the water, and our molecule is which is amphipathic, like the head, the polar head, and a tail, which is non-polar. It will tend to put the head, which is in the water, inside of the water, and the tail will be exposed outward. Why should we waste time and think about this? Because the membrane of our cells are made up like this. The membrane of our cells, they're principally made up of lipids and fatty acids like this, which are called phosphoric lipids, which have two tails like this of this type. These two tails like this, which are not mixed with which cannot mix with water, and another group here, the glycerol side of and a head, a polar head, which is connected to phosphorus, which is polar. And this image that you see here, which is depicted and represented, is a representation of how our cell membranes are made up, which has a double strata of these fats. This is what we see inside the cell, and this is outside of the cell, the external part of the cell. The external part of the cell is watery, and the inside of the cell is also watery. The head will tend to be oriented to the watery external, and these are the fatty acids, which tend to fold in. Now, under the electron, now if we look at the plasmatic membrane, if we look at it with an electron microscope, we can see this. And it is an isolating element which isolated this fatty part within,
Mi scusi,
and it
professore.
isolates the
Posso-
external from the internal part of the cell. Yes,
Allora,
Father.
ho perso lo schermo suo,
I
non
lost
lo vedo più.
I can't see your screen. Can others see it? I see it. I see it. I can
Sì,
see
se
it.
vede, se vede.
Yeah, we can see it. This is just the last slide that I'm going to leave to. I don't know what to say to you, Father. The translator can see it as well. The translator sees it fine. Translator can see it. Okay. Might be. We were saying that in this strata, which is isolating strata, which is made up of this double fatty strata, it allows the cell to communicate with the external world and to be to create channels with the external environment. Water, we said in the afternoon. You can look at the videos in order to develop your idea of how water works. We talked about hydrophilic, hydrophobic, and amphipathic molecules, and then we talked about hydrogen bonds versus ionic bonds, and then covalent bonds. Hydrogen bonds, as such, it acts as a kind of a bridge between two molecules, which has a different electronegativity, and it is the weakest type of bond. Now, there are other bonds which we're not going to deal with. There are other forces, but these are the most important bonds for us. Now, when we look at DNA bonds, you know that very often you've heard of DNA. It's a molecule which is made up of a double helix. We speak of the double helix of the stairs of this of its staircase, spiral staircase, are made of hydrogen bonds. It's not such a strong bond. All of them together are strong, which happens in water. Each of them is easily broken. This is what happens in our DNA, which is tomorrow we will see. It's a kind of zipper closure, and it's not so resistant. We often mention this. Sometimes our zippers are break. Doesn't always work perfectly, but very often it does work. In this image of what we see today above, we'll speak about hydrogen bonds that we see in our double helix structure of DNA. Okay, we'll take I know that's a little bit heavy for you. It's a lot to absorb, but I will flesh this out a little bit more tomorrow when we talk about this. We're going to talk a lot more about DNA and hydrogen bonds tomorrow, and how the molecules come apart and come back together. I think we can stop here.
Volevo chiedere solo una cosa.
And now tomorrow we're going to meet again.
Una cosa,
Yes.
solo le registrazioni, da dove si possono prendere poi delle
where can you
lezioni?
get them?
Da
Where can we
quale-
get them? That's a good question. I don't know, in the sense that I am the coordinator of the Friday course, which will be recorded. That's put on the the General Casa, I think, and Father Miranda, they record them in different languages, the courses. I think that they are made available not during the course, but in the course material, in the upra.org course. I think there's an area that's only dedicated to the video recordings. I'm not able to answer that. In different courses, it's done a different way. but I think all the lessons, the images are all available on the intranet, on the
No,
upra.org,
nella pagina,
on the page of the
professore,
course,
nella
professor.
pagina
There
ci
is
sono tutto il compendio di tutte le
the
lezioni
compendium of all the lessons
della
of
settimana intensiva
the
e
intensive
lì
week,
viene
and
anche la
there
registrazione.
the recordings are also placed there on the page as
Sì,
UPRA
quando uno
courses, right?
entra
UPRA
e
courses.
cerca
You
licenza
enter and you
bioetica,
look for license
va a settimana
bioethics,
intensiva e
and we
lì
go to the
è
intensive
tutto,
week.
diciamo.
On the web page,
Sì.
yes. That seems strange to me because that with a person who's not a
No, se
student
capisce che deve entrare alla
access it.
parte
We understand that
riservata
we need to
con
enter
il
into the
password.
reserved part.
Sì.
Of course, yes. Perfect. Thank you for explaining that to us, Father. Okay, very good. Thank you. Okay, have a nice evening. I hope that I will not cause too many nightmares to you tonight, any nightmares that involve molecules and liquids, etc., etc. Okay, so we'll meet again tomorrow.
Regina degli Apostoli.
Ora pro nobis.
Mary, Queen
Grazie.
of the Apostles, pray for us. Thank
Domani.
you, and we'll meet each other tomorrow again. Excellent.